what, Tuesday? Noon now? Anyone else? Yes? You're folding it?
No.
What the?
No, so it gets worse than you think. So I did them, I believe, right, but I stapled them backwards.
Okay.
So that says a lot.
All right, anybody else?
Yeah, I put C on top. So.
How was that? What did y'all think?
B was not bad. C is, it was cool, but
I don't know if I want to turn this in.
Okay.
I have two different options for C.
You got to decide. Yep. What are you going to do?
I don't think it's going to be better.
Okay.
there's only two problems.
Two problems.
I don't have a stapler though.
Just make sure your name's on the first one. Is that it?
First one.
Okay. That's not part of it?
It's the other option.
Okay. Are you turning in? Are you turning? Yes? Okay. All right, let's get moving here. So we were finishing up Power Series, and we ran out of time, so I didn't do B and C, and that's what I asked you to do for a quiz. So just out of curiosity, what was the radius of convergence for B?
Negative, oh no, sorry. 3. It was 3. Yeah.
So the radius convergence was 3, so there was an interval.
Yes.
Were the endpoints included or not?
No.
Both were not?
No.
Okay, I'm just asking. I haven't worked this problem in a while. I'm just seeing as a consensus, what the class got. So a lot of you got interval with no endpoints. How about this one? So the radius was infinite?
Yeah.
So, okay, all right. We'll see. We'll see. All right, we are moving on to 8.6. Now, 8.6, we can, are you turning in or not?
Yes.
You are? All right, now, please turn in now. So this section, we could really get ourselves bogged down in because there's like these really cool examples we can do. I've got to be kind of careful about how far I go down the rabbit hole for this because I really think the next section is more important. So I'm going to spend some time, but I'm going to have to trim the homework assignment a little bit to take out some of those more interesting, complicated problems. All right, so where are we at this point? We know, well, now that we know what a power series is, right, and how to determine the interval of convergence and radius of convergence, thank you, we are going to try to attempt to take some functions that we already know, right, and rewrite them in power series, as a power series. But here we're going to be very limited on what we can convert over, right? This is going to be a very limited view of conversions. So let's look at the main formula for today, and that is the geometric series that we talked about last class, that as long as the absolute value of x is less than 1, then this geometric series will converge, right? And it converges to, what does that converge to? Uh-oh. Uh-oh. No?
Depends on what x is.
Well, I said if absolute value of x is less than 1, then this will converge.
To 1.
No. It's like a geometric series with a being 1 and the r is the x. What is geometric?
A over 1 minus r.
A over 1 minus r, but for us a is 1 and r is x. So this converges to 1 over 1 minus x. 1 over 1 minus x.
Wasn't x 1?
No. Absolute value of x is less than 1. Right? Less than 1. So we've already determined that, right? I'm going to write this on the side over here. That if the absolute value of x is less than 1, that the sum n equals 0 to infinity of x to the n will equal 1 over 1 minus x. I showed y'all this. Remember, it's the very first example I showed you where the picture became the other picture, but it only worked between -1 and 1. So we're going to use that, and that's all we're going to use today for this section. For this section, I should say, not today. So as an example, I would like for us to express, and make this a little bit bigger. I'd like for us to express this function, or this expression, 1 over 1 plus x squared as a power series. All right, so what the heck am I talking about? Well, I know that this 1 over 1 minus x, I know that I can rewrite that like this, right? So long as the absolute value of x is less than 1, this can become this. So I'm going to just like, what? Huh? Yeah.
Did you just add 3 to the x over n? So is it x over n plus 3?
Is mine up mark? Am I full of it?
No, that wouldn't change, that wouldn't give you this. Because this is not a sum, right? Do you see this is not a sigma? There's no sigma here? So watch what I do on this first example. Do you all agree that this is this? That's the same thing, right? And then if I look at it that way, this right here is kind of like the x is over here, isn't it? Do you all see that? Like if you squint your eyes, this is like, I mean, well, maybe I'll do it this way. Replace this with u and replace this with u. Then the negative x squared is like the u is over there, isn't it? We have 1 over 1 minus u. And, yeah? I'm seeing squinting eyes. Squint more. This is true so long as the absolute value of u is less than 1. It does not matter what the u is. All right? It could be u, it could be x, it could be x squared, it could be anything. All right? So what I did is I rearranged this or kind of massaged it to make it look like that. Here, I can say if the absolute value of the negative x squared is less than 1, right, which is the part that's in the parentheses here, if that's less than 1, then this will become the sum n equals 0 to infinity of what? U to the n, right? But what's u for us? Negative x squared. Negative x squared to the n. And that's it, but I'm going to clean this up a little bit more. This is the same as sum n equals 0 to infinity. Let me split this apart. I'm going to look at that negative x squared as negative 1 times x squared. And I'm going to raise each of those to the n power. So negative 1 to the n, and then x to what power? 2n. There we go. I've converted this expression into a power series. So as long as you give me an x that satisfies this, that if I take the absolute value of the x squared, as long as that's less than 1, then you could, instead of writing that down, you could use that power series instead.
So the only thing you could really take is like...
Yeah, there's some small numbers. Yeah, it's a very small interval. It doesn't seem very useful, does it? But that's not the point. The point is that we have a way of converting something that is not a power series, right? This is not a power series. That could be like a function that I could ask you to graph. We can convert it to its power series, which we could then start graphing that, and then hopefully they start to look like one another. At least on the interval of convergence, they would look the same. All right, find the power series for this. All right, that does not quite look like this, does it? Because we have an x to the 4th on top, right? So I'm gonna do this first. Do you agree with that?
Yeah.
I switched the 5 and the x on purpose on the bottom. I switched them because on the formula it's 1 minus u, isn't it? And I would like to eventually get this to be a 1 minus something. The x to the 4th, I just peeled it off to the side. Now this equals, let me pull a 1/5 out of, I should say it this way. Let me factor a 5 out of the bottom. I'll leave a 1 on top. I'm factoring a 5 out of the bottom. If I do that, it turns into a 1 plus what? x over 5 or 1/5 x. Either way, you can write it either way. So if I distribute this 5 through, I get back that, right?
Yeah.
See, what I'm trying to do is trying to get it to this. See, I'm trying to slowly turn it into this. That's equal to, let me bring the 1/5 out in front of everything, x to the 4th times 1 over 1 minus negative 1/5 x. You'll see that? I did a minus minus so it would match that formula. So I can turn this into the power series now so long as what's true. So if, what do I need to be less than 1 here? The negative 1/5 x, right? The thing that's here, the absolute value of that must be less than 1. So if that's true, then I can say the next line, right? So I'm saying if this is true, then this is equal. It's 1/5 x to the 4th sum n equals 0 to infinity of u, right? For us, u is negative 1/5 x to the nth power.
Why doesn't the other x going,
Where?
that 1/5 x to the 4th?
I'm going to put it in here in the next line. Yeah, I'm going to. But over here, I just peeled it off, right? Because what I'm trying to do is get something, right, that looks like this. Trying to make it look like this, right? So I needed that x to the 4th off the top. I needed the 5 out of the bottom. And then I can make it look like this.
And the x and the out's not a problem.
It's not a problem, but I'm going to put it all together, though. Because a power series, you don't want things like x's out front. You want all the x's in here. You good? Okay, I'm not done. This is equal to 1/5 x to the 4th sum n equals 0 to infinity. Okay, I'm going to apply, because again, this is multiplication, I'm going to apply the n to both of these again. So this will be negative 1/5. Negative 1/5. Geez, come on. Negative 1/5 to the n, x to the n. All right? Any questions there?
Oh, I see, pull the x out.
I did the nth power, since this is multiplication between these two, I did the nth power on both of them, right? Now what I'm going to do is I'm going to bring this in to the sum. So let me write the next line down and see if you follow. Sum n equals 0 to infinity. I have negative 1/5 to the n. I have x to the n, but I brought in a 1/5 x to the 4th. The next line, I'm going very slow through this. I'm going to do negative 1 to the n times 1/5 to the n times x to the n plus 4 times 1/5. So on that line, I'm trying to do this in pieces so you see where everything comes from. I'm splitting this up, negative 1/5. I'm writing it as negative 1 times a 5th, and then I'm doing the nth power on each one of them. What I'm essentially doing is getting that negative 1 out on its own to the nth power. This becomes that. I put the two x's together, right? They both, one's x to the n, the other one's x to the 4th, so you add the exponents, and I still have the 1/5 there. Last step. I'm going to put the 1/5s together. Sum n equals 0 to infinity. Negative 1 to the n, 1/5 to the n plus 1, and then x to the n plus 4. There you go. That's your power series. Also, what did we need for this to be true? For that up there to turn into this, what did we need?
The absolute value be less than
Absolute value of what?
1/5.
Negative 1/5. I can't do a 1/5 today. Negative 1/5 x. I need that to be less than 1, right?
Yeah.
Which is the same as saying 1/5 absolute value of x must be less than 1. I just took the absolute value of the negative 1/5. which is the same as saying the absolute value of x must be less than 5, because I can multiply both sides by 5. So this is actually anywhere between -5 and 5. This thing will be convergent. This expression here is equal to this expression here, so long as you're dealing with a number that's between -5 and 5. Yes?
Wait, so, no, when you're multiplying the n fraction,
Yes.
won't you have to switch the signs? Or is that what-
Well, I'm doing this line right here from here to here. What I'm doing is I'm taking the absolute value of each one. And when you take the absolute value of the negative, it becomes positive. And then when you multiply, you flip inequalities if you multiply or divide by a negative number. I did 5, so I don't have to flip anything. Yes?
So the goal when you're making these series is every number inside of that sum has to have a power? Is that what
You just, like, I didn't want to leave it like this because this is 1/5 to a power, that's 1/5 to, you know, it's like put them together, you know? That's why, and how did I get this 1/5? It came from the negative 1/5, right? I couldn't put these two together right here because they're not both negative,
Okay.
right? If they were both positive, I could put them together. If they were both negative, I could put them together. But to get it to work out like this, I had to peel the negative one off.
Makes sense. I was just wondering at what point you considered it correct, like what
You could argue it's correct here,
okay.
because it is. I mean, it is correct. It's correct before I even move the stuff in. It's correct. It's just a different form. I'm trying to get it to look like the way you'd see it, like in the book or in an answer. Yes, sir.
The 1/5 x to the 4th, that was in back, so you just brought that to inside the sum?
That was in the front here, and I brought it in. Yes. Yep. Okay, so this works only between -5 and 5, right? Now, I didn't do this on the previous problem, but let's write out the first few terms. If n is 0, let's see what we get. If n is 0, that's 1, right? 0 here for n, you get what? 1/5, okay, and then x to what power? X to the 4th. Plus, okay, now let n, oh, no, it won't be plus, will it? N is going to be 1 now. So if n is 1, negative, so that's why it's going to be minus. And then you get 1/5 to the second power, so 1 over 25 x to the, what is it? We're plugging in 1, right? So 5th power. See what I'm doing? Plus, the next one will be plus because we're now letting n be 2. 2 here, -1 squared is positive. 2 here, what's 1/5 to the third power? 1 over 125. X to the 6. And the next one will be a minus, right? But I'm just going to put plus ... because it keeps going, right? So what we're saying, okay, this is what we're saying, is that if you plug a number between -5 and 5 into this, you get the same answer as plugging the number between -5 and 5 into this. So like if we plug the number 1 in, what do we get if we plug 1 up there? 1 over 6? 1/6 is the same as plugging 1 in here, which would be 1/5 minus 1/25 plus 1 over 125, right? Minus the next one would be 1/5 to the next power up would be 625. Do you see that the x powers just keep giving me a 1 every time I plug 1 in? So if you do 1/5 minus that, plus that, minus that, and you do that forever, it's going to converge to 1/6. I'm curious, I'm going to go to Wolfram, and I'm just going to type in the original problem, x to the 4th over, where is it? What was it? X plus 5, that was it? Yeah, okay, so if I type that in, let's see, Wolfram will tell me everything, like a bunch of stuff about that. It says, there's your input, it plots it, draws me a picture, and check that out. Alternate form. Whoa, what? Did I type it in right?
That's what my answer is going to look like.
Hold on.
I think you just factored it.
No, something's wrong. x to the fourth, or x plus 5. No, that series should be the same. Oh, there it is. Okay, it was expanded somewhere else. That's it right there, series expansion. So x to the fourth over 5, right? Minus x to the fifth over 25, right? So it's giving me the alternate series form of that expression. Yes?
What does the O mean? I see that a lot, but I don't.
Big O has to do with like that. It's stopping at the order of 9. So big O means a lot of different things. And in computer science, it's like a way of counting operations. But yeah, that's yeah. It's not as simple like, oh, big O is that. Yeah.
5.
Yeah, 5 exactly. All right, good. Get the basic idea. As you might imagine, we're pretty limited on what we can use that for, right? Like the thing we're trying to convert has to be able to be turned into this. And I mean, there's a lot of things that we would never be able to turn into that. So it's nice, but it's kind of, eh. So we move on. All right, this is a big deal here. We're going to talk about differentiation and integration of power series, because this is really why we like power series. They're easy to differentiate, they're easy to integrate. So I have the note here. I think it's always better when I just develop it, ourselves. So a generic power series, right? A power series about x equals a has the generic form sum n equals 0 to infinity c sub n x minus a to the n. That was the generic formula for a power series centered at a from last class. If we start writing the terms out here, we get c sub 0 plus c sub 1 x minus a plus c sub 2 x minus a squared. I'm going to go a couple of these, all right? C sub 3 x minus a to the third plus c sub 4 x minus a to the 4. One more. C sub 5 x minus a to the fifth. That's the generic power series, right? And if it converges, right? If it converges, it either converges at a point on an interval or everywhere, right? Right? Okay, so we have now that, let's say that we have this power series and we define a function to be that power series. And I'm only talking about it where it converges right now. If it converges, then what would the derivative of this be? So let's try and take the derivative of this function. Let's ignore that for right now. Let's just start taking the derivative out here with respect to x. So what's the derivative of some constant? 0, right? Okay, here, that's a constant, right? What's derivative of what's in here? 1 minus derivative of a. A is a constant as well. So 0, so 1. So derivative of what's in there is 1, and then times c sub 1. So we get c sub 1 plus, okay, what would happen here? Constant, the variable is squared, right? So you have to use chain rule. 2 would come down in front of the c sub 2. Then you would have the x minus a to what power? 1, because you bring the power down, right? It's still there. And then you have to do chain rule, derivative of what's inside. What's the derivative of what's inside there? 1. It's 1, right? You got that? Yeah. Plus this one.
Yeah, 3 comes down.
3 comes down. C3
Times x minus a squared.
Squared, and then chain rule, derivative inside 1. So that's it, right? And then we just keep going. This will be 4 c sub 4 x minus a cubed. And then finally, the last one, well, this should have been plus dot, dot, dot up here. 5 c sub 5 x minus a to the fourth, right? You got it? Now, I'm going to challenge you now to see if you can find a sigma notation for that. Sigma notation. So let's see. We start at C sub 1, right? And then C sub 2, C sub 3, C sub 4. So if I let my index start at 1, let's just do it at 1, then I'm going to have C sub n, right? That would give me this piece, this piece, this piece, this piece, that piece, right?
Yes.
Yeah, so in front, what goes in front? We want 1, and then the 2 is matching, the 3 is matching, the 4 is matching, right? So an n in front of that times, now they each have an x minus a, right? But the power on those is 1 less than the number in this index here, right? So that's 1 less, that's 1 less, that's 1 less, that's 1 less. And then what about here? We don't have it here, do we? It's to the 0 though, right? Isn't that to the 0? So I'm going to have here x minus a to the n minus 1. And I'll go to infinity, right? Yeah. Which is exactly what you would think would happen if I just ask you to do the derivative on that instead of all that, right? What happens? You bring the n down, right? And you subtract 1 from there, and you get this, right? Now, there's one difference. This index starts where? And this one starts at 0. So when we do this, we either need to just remember to change the index to 1, or do we really have to change the index to 1? Could we have said start at 0? Does it change anything? Why doesn't it change anything?
First term is 0.
Because if you start at 0, your first term's 0. Exactly. If I start at 0, then that 0 times who cares, right? So changing the index back to 0 makes no difference because it doesn't change your sum. Now, I think in most problems that I do in the homework solution videos, I always I leave it at 1. But just so you know, you can switch it to this, and it doesn't change the sum at all. All right, understand? All right, so that's the differentiation of a power series. That's how we take derivatives. We just do it the way we normally do derivatives. How about integration? Let's go back. Let's start with this up here again. So if I ask you to find the antiderivative, right, with respect to x, well, we know we're going to get something plus a constant, right? You always have a constant when you do integration. So I'm not going to be able to do plus constant because I'm going to have dot, dot, dot forever, right? So normally when we do integration of power series, we put the c in the front. So I just say c plus. Because I know there's a c, I just may as well throw it out in the front of the whole thing. And now I start doing the antiderivative of this. So what's the antiderivative of a constant? Constant times x, right? And then plus, okay, this one, what's the antiderivative of that? Let me save us some time. How about this? Isn't it that?
So you're treating that as the x?
Yeah, this is basically like the x and there's a constant in front, right? So you're doing like a power rule. This is like x to the first power. So it's 1/2 x squared, essentially. And if you don't believe it, just take derivative of this. You should get that. And the next one should be 1/3 c sub 2 x minus a to the third, right? And then you just keep going. So can we come up with a sigma notation for this one?
Yeah. Would you put the c in front of the sum or not?
Yeah, put that c out here. You can do it at the end also because the sum will be contained right here. Then you can just say plus c, but there's nothing wrong with putting it in the front. So I start out c sub 0, right? Then c sub 1, then c sub 2, then c sub 3. So I'm going to start my index at 0 as well. C sub n. X minus a to the n plus 1.
Over n.
And then over n, what do we have in front of all of these? It's not, is it n?
I was gonna put the whole thing over n.
N plus 1. Now, let's just check this because is that working? If n is 0, what happens here? What do you get there? 1, c sub 0. And then we're plugging in 0. You get x minus a to the 1. Wait a minute. If I plug in 0, I'm getting 1 times c sub 0 times x minus a to the 1, right? That's what I'm getting? That's not what I have here, is it? Do y'all see that's not what I have? So you might think this isn't right.
Well, I mean, but.
Hold on. No, a is not 0. A is arbitrary, right? A is arbitrary. So it looks like I'm wrong. However, distribute the c sub 0 through and tell me what you would get. C sub 0 x plus c times a, right? And what is c times a? It's a constant. And don't we have a constant out here anyway? So I could just move this constant out with the other constant, and now it looks the same. So this is okay to have. Even though it doesn't look like that, it actually is some version of these two put together. And then the rest of it works, right? If n is 1, I get 1/2 c sub 1,
Yeah, that.
and then x minus a to the 2. So it works the rest of the way. But do you all see that's exactly the power rule on this? Like, you know, we did the derivative, we just said bring the n out and then subtract 1. Isn't the power rule for integration in Cal 2, isn't that like in the beginning of this class? You add 1 to that power and you put 1 over n plus 1 in front? Same thing, right? That's exactly what happened here. So this is just to illustrate that you have the same exact thing happening that we've been having happen this whole time, that everything kind of translates into the power series, which is good. What the hell is that? Is that rain or is it drums? It's not raining, right? It's real nice outside. It's a festival. Everybody's having fun, except us. There's that Jacobian, Bessel function, sorry. I'm in the wrong class, sorry. That's that Bessel function that we did last class where we found the interval convergence, radius of convergence.